How's it going? This is Will Sutherland doing Lab 1 Constant Velocity. So, in this lab, we used Newton's first law and Newton's second law mainly. So, where Newton's first law is that states an object in motion or at rest will stay in motion or at rest unless acted upon by a net force. And the second law, Newton's second law, is just saying the net force or the sum of the forces is equal to the derivative of the momentum respect to time, which is the same as mass times acceleration. So in this lab, we rolled a marker across a flat table at as close to a constant velocity as possible. And so what we wanted to use from that is to test Newton's first law using Newton's second law, comparing the predicted positions of the marker over time to the actual positions of the marker over time. And also just was to better understand the relationship between the system and its surroundings. So in this case, our system is simply our mass or object, the marker, and the surroundings are everything else. So it's going along in the x direction. What we need to know to find predicted positions of the marker over time, we need the average velocity of the marker as it travels across. So we used Tracker to do this, so where we plotted the position versus time, and it also plotted the velocity in the x direction. So we simply took the average of those three velocities there to give 0.2307 meters per second, which is important for this. For setting up initial conditions and understandings. So, as I just said, initial condition for velocity 0.2307 meters per second, as you can see right there. What is important to understand is that remember Newton's second law states the sum of the forces equal to mass times acceleration, and acceleration is just the change in velocity over change in time. And since this is at a constant velocity, change in v equals 0, then that means acceleration is equal to 0, which therefore means the sum of the forces must be 0. This is important for our time loop, which I will talk about in a second. I also said that the position of the marker was at 0, 0, 0, at starting at time 0, with a delta t change in time of 1. So, finding the predicted positions and velocities. Found this velocity. We were able to use Newton's second law again to get it out into its to find the v final from v initial, because again it's just change of v over change of t, separates that out. Then you just do a bit of algebra, boom, boom, boom. And again, we know that the sum of the forces is equal to 0, so therefore v final is just equal to v initial. And this is shown right here. We're just saying plus 0, 0, 0 for a vector for our velocity of the ball update. The position is a bit different. The position is just, you just do average velocity equals change in x over change in t, x final. Do this, separate it out. X final equals x initial plus v average velocity times change in t, as shown there. And then keep in mind this is when t is less than 4 seconds, and this is doing it every 1 second, every delta t. So there should only be really 4 values that are actually plotted, but it plots in this straight line, as you can see here. The position time of our predicted graph. So finally, we needed to compare these predicted to the experimental, and they are pretty much identical. The predicted is only a little bit lower than the experimental, which could have been maybe because of if there was some sort of like dip in the table that very small that would cause it to be a bit to cause it to accelerate a little bit, so that the velocity would be somewhat higher. But it is so small that that it doesn't seem to be the case. So one question was whether or not we could count up all of the forces acting on it to add up to the net force of 0. And for that, you cannot really, because there's too much uncertainty in the way we set up this experiment. Because there could have been, for example, there could have been a air conditioning unit or a vent or something that was just blowing air, that, or there might not have been, that could or could not have added to that net force to be 0. So it's not possible. And another question: what would happen if you changed positive x to negative x in the tracker? This would have the only thing it would have changed was it would not have changed the magnitudes of the velocity, or the actual magnitude of the position, the distance traveled. It would just change. It would only change the direction. So this would be going in the negative direction, like that, same velocity, same slope. So that is that. So in conclusion, Newton's first law is verified. The marker moved at a relatively constant speed in the x direction. The predicted positions of the marker were almost identical to the actual positions of the marker over time, showing that the net force on the marker was 0. And it also showed the importance of setting initial conditions and constraints to getting the results you need. So thank you.